Now you'll recall that with our original data, we calculated the average rate of change of y with respect to t for each of these intervals based on the observations. Now there are obviously some errors involved in this, some uncertainties, but we do have a more or less steady progression. When we graphed the data, we estimated a line of best fit to be rate equals 0.10 t plus 0.5. The rate, in fact, is the velocity, the average velocity, the rate function, the function that models these rates versus the midpoint clock time should be a good approximation to a velocity function, because when we divide a delta y, which is a distance or displacement, by a delta t, which is a time interval, when you divide distance moved by time interval, you get speed. Or more precisely, if you more generally, if you divide a change in y by delta t, you get velocity, and velocity could be positive or negative, whereas speed can't. In any case, this line then tells us that the velocity model is 0.10 t plus 0.5. Now, is this velocity model consistent with the position model that we obtained? The position model that we obtained for the position of the ball. Position is a function of time. Well, it turns out, and if you know calculus, of course, if you're a Math 158 student, you probably don't. But there's kind of a neat little calculus connection here. If y equals 0.07 t squared plus 28, then the corresponding velocity, and if you do know calculus, you're simply going to take the time derivative of your position, you're going to get your velocity. And there are simple rules for doing that. The rules for taking derivatives of many functions are quite simple, but you have to know what all that means. So if you don't know what that means, that's okay. There's a connection, and if you ever take calculus, you might come back and look at this. If you've had calculus, you should understand this connection. So then, if y equals this, then the velocity ought to equal 0.14 times t. Now, our velocity model was v equals 0.10 t plus not 0.05 but 0.5. Okay? Now 0.5 is a fairly small number, but it's not insignificant. And the 0.10 t is pretty close to the 0.14 t, but not exact. If these models were completely accurate, this would mimic this. This would be the same as this. The velocity function that we get by taking the rate of change function, which is the derivative function, would match the velocity we get when we do a curve fit. Now, there are several sources of potential error. When we did the curve fit for the data for the quadratic, we could have been off in many ways. And when I did this curve fit, the curve fit for the rate of change versus midpoint clock time, I said already that we probably should have made that graph a little steeper, which would have increased this 0.10 up to maybe 0.12 or so, and would have decreased this 0.5 because the y-intercept would have dropped a little bit. And this model would have then been closer to this one. But even if you do the absolute best fit and the absolute quadratic best fit, these aren't going to agree unless the thing that we're observing can really be modeled by a quadratic function. And the data we have here doesn't look like it's all that amenable to modeling by a good quadratic function. Again, because perhaps I sped up the count, perhaps I was a little bit late every time in determining where the ball was, There could be many, many reasons that this model could be off. In any case, this should give you a pretty good picture of the modeling process and how it can be conducted.